But the most important thing that you can do as a weightlifter is literally do the motor control, the motor coordination warm up, already lifting to absolute maximum and going to reasonably heavy weight. Might not be the weight you use on the platform, but reasonably heavy. And if you do something else, you can seriously affect it.
Hi, Tony. Welcome to Evidence Strong Show. If you could briefly introduce yourself.
Yeah, hi everyone. Yeah, it's great to be here. Thanks for the invitation.
Thank you.
My name's Tony Blazevich. I'm a professor in biomechanics, although these days I do quite a lot of research also in the neurophysiology space. In the biomechanics space, I guess I work mostly in understanding how muscles function, and that's why, of course, we have to have the nervous system involved. Although in athletes, I also work at the whole body level, how to run, how to change direction, how to move, and of course, all the strength and conditioning aspects to that. So I guess primarily I'm a researcher and a teacher in academia, but I'm lucky enough to continue to work with athletes on the side.
All right. And today we're diving into post-activation potentiation and post-activation performance enhancement. So let's define the terms so we are on the same page.
Yeah, good idea. Maybe 100 years ago or more, it was already recognized that if you electrically activate a muscle once, you get a certain force. And if you activate it a second time, we get more force. And it's taken about 100 or so years to understand exactly why that's the case. But right down at the molecular level, when actin and myosin cross bridges in your sarcomeres are generating these forces, we seem to get a little bit more force because we get some more cross bridges between the actin and the myosin attaching if you've already done a contraction before. And we might call that classic potentiation. That force is potentiated, so it's higher. And you can see that in the muscle itself. Now, there's still some debate around the exact mechanisms and everything else, but we can discuss that if you really, really want to. On the other side of the coin, a lot of people then say, well, if the muscle generates a bit more force after the second or third contraction, maybe we can do that as well in normal human movements. Like when we're warming up, we might be able to do these funky high force contractions. And then when we do something after it that requires force or power, maybe we're going to be better. And a lot of people call that potentiation as well. So it gets a little bit confused between real life whole human potentiation and this little molecular thing happening in our muscles. So maybe about 5 or 6 years ago, a group in Canada decided to call it performance enhancement rather than potentiation, just to distinguish it. So what we call post-activation performance enhancement, or PAPE, is really that sort of global improvement in performance you get if you've done something a bit tough before it. So most of the time in weightlifting or in the gym, we're talking about performance enhancement, that PAPE thing. Let's say you're a weightlifter. Your job is to stand on a platform with a very heavy weight and somehow get it from the ground to above your head. That doesn't just require maximal muscle strength, okay? Because what you need to do is induce momentum or velocity in the bar. Because at some point, you need to do essentially 2 or 3 phases of lifting. And in order, for example, to get underneath the bar, you need the bar to keep going upwards like a projectile, like a ball being thrown. To give it that speed to keep going up against gravity while you then duck underneath it to do the second or next phase of the lift, we talk about needing muscle power more than pure strength. As a biomechanist, I'd say power is a really difficult, complicated, and often erroneous term. I would say we need to give kinetic energy to the bar. We need more energy in the bar. So the question is, how do you do that? And let's be really clear here. You need a nervous system that is appropriately, but as maximally as possible, activating your muscles. And just remember that in a really complicated movement, it's not just a case of maximally activate every muscle. You have to time the activations and scale those activations to generate very specific directions of force. It is a hugely complicated task, which is of course why it takes years or decades to get really good at it. The next thing we need is then for the muscles to do their job. That means, yes, they need to produce a really high force, but they somehow need to shorten very rapidly. And by the way, while they're doing that, they're stretching and then allowing the recoil of elastic elements like tendons to get extra kinetic energy or power into the system. So we need the nervous system to do its job. We need the muscles to do its job. Now let's go back to how we get there, besides the fact that you've now trained for years or decades to get it right. And let's just talk about in the lead up to that event, what PAP would say, like if people said post-classic classic post-activation, the real muscly thing. What seems to be happening there is if you can activate the muscle really quite hard, it needs to be a high frequency of pulses coming from your nervous system. What seems to happen then is the calcium that your muscles then release triggers a series of processes that bends the myosin arm closer to the actin site that it needs to grab so that it can pull your muscle. So when myosin wants to pull your muscle, it's kind of randomly looking around for it. It doesn't happen just because it happens. It's like a random thing, like everything in biology or physics is random. And when you release calcium, the actin is ready to take the myosin, but the myosin doesn't just automatically attach. It really helps if the myosin comes closer. And when you've activated the muscle once, it turns out that those myosins stay closer. So when you activate it the second time, they're more likely to bind and pull. So the current mechanism behind this classic post-activation potentiation is that the myosin is more likely to bind when we release calcium. So they call it calcium sensitivity. We're more sensitive to the amount of calcium. And if we take a single muscle fiber, we see that. You activate it and you can see all this happening. It's not just about the myosin itself. There could be water, there could be some temperature effects, but mostly that's the reason.
Just a clarification. So when you talk about myosin and actin, what you're referring to is the sliding theory. So to contract the muscle, these two have to come together and kind of slide on top of each other.
That's exactly right. Thanks for clarifying that. So in your muscle, you've got muscle fibers. Inside the muscle, your fibers, you've got these thing called myofibrils, these long chains of motors. Those motors are called sarcomeres, and you've got literally trillions of sarcomeres in any muscle. But the rows of sarcomeres are all shortening at the same time. And the reason they shorten and therefore shorten the whole muscle is because within them, you've got these micro motors where a myosin protein or a filament is attaching to an actin protein and pulling on it. And this shortens each sarcomere. And when each sarcomere shortens, those myofibrils and therefore the whole fiber shortens. And of course, this is where we get muscle work from. And so what we're saying here is that if you just activated those myosins to pull on actin once, then in the seconds or maybe a minute or two afterwards, they're going to do it a little bit better. It seems to be more effective in fast twitch muscle fibers than slow twitch muscle fibers. It's almost like an evolutionary thing where you don't just want a random single twitch from the brain or something to over-activate you. So if you've just activated once and it looks like you're going to need your muscles again, it's like this little compensation thing comes in and allows the fibers to actually do their work really, really well. Now, I just want to be really clear here. If you activate the muscle and get this mechanism working, this classic post-activation potentiation, it works immediately. So if you immediately do another contraction, you'll see an improvement in performance. But it has a half-life of around about 30 seconds. So in other words, we lose the ability really quickly. And by 2 or 3 minutes, it's completely gone. In other words, the classic PAP is happening early, but the potentiation that most people are seeing in these research studies is happening much later. So it's almost certainly not due to classic PAP. And in some ways that makes sense. Let's go back to weightlifting. I said you need your brain to activate, spinal cord to activate, you need massive activation, you need whole coordination, you need a huge number of muscles doing lots of things, and lots of things in your muscle, temperature, water mass, everything will affect how forceful they are. Maybe it makes sense that a little teeny mechanism that's happening in your fiber level is not as important as we first thought. So when it comes out to your entire weightlifting capacity, it seems really unlikely that this classic PAP is actually doing much at all, especially by the time you walk out onto the platform, center yourself, image the lift, and commence the lift. You've already lost most of the effect anyway. My opinion is that this classic potentiation that happens down at that sort of fiber level is probably not really important to us from a muscle strength and power perspective. And I know a lot of people might disagree with me, but like I said, the peak of that effect happens in the first few seconds, and by 30 seconds, you've already lost half of it. Yet, we're often performing a long time after that. And in the research studies, the peaks that you see, which we definitely need to talk about, tend to take minutes to come. So it's coming when this mechanism is completely gone.
So you mentioned that the water content in the muscle may play a role. So I wanted to explore this part.
So, of course, the research already shows us that once you're dehydrated, we seem to have reduced neural outflow. So your brain and spinal cord don't seem to activate the muscles maximally once you're dehydrated. So we're clearly sensing dehydration at lots of levels of the body. It could be everything from changes in blood pressure to changes in the pressures within the muscle that affect some of the sensory information coming back to us. And that seems to be affecting the outflow to the muscle. So first of all, if you're cutting weight and you're weighing several days prior, you really need to rehydrate from a nervous system point of view. But we've also known for, since at least the 1960s, that again, down at the muscle level, certainly at the fiber level, but it looks like even at the whole muscle level, water content matters. And it matters for two main reasons. One is during the eccentric phase, if you've got lots of fluid in the muscle, the cells are what we call more turgid. Just like if a plant is dehydrated, it wilts. It gets soft, your cells get soft and floppy. The same thing happens in your muscle, that if you don't have enough water sitting in the muscle, the cells themselves get a little bit more compliant, a little bit floppy. And what that means is when the muscle's being stretched under load, if you want to stretch a balloon, for example, it has to get narrower in its center because the volume stays the same, right? So if you pull it out this way, it has to go shorter this way. Same with your muscle. If you want to stretch your muscle outwards, it needs to shrink inwards. If you've got lots of water in there, it's harder to do that. There's more pressure. There's more resistance to that, which actually makes it harder to stretch your muscles. Any of your listeners who've done really high intensity exercise where we get massive water flow into the muscle will know they feel stiff. Anyone who has had DOMS, delayed onset muscle soreness in the days after a session knows that the muscle gets stiff. And a lot of this stiffness is the water mass that's sitting in there, and it's being dragged in there by all these molecules like lactate and all these other ions that are drawing the water in. Now that increases eccentric strength because it makes it harder for the muscle to stretch. So in one way, just having water seems to be beneficial for reducing stretch. But when it comes to shortening the muscle and generating power, we think it also has two main mechanisms. One is the fuller and stiffer the fiber is, when the fibers shorten, they then bulge, and that forces the other ones away and causes rotation of our fibers. Yeah. So muscles don't just shorten end on like this. The fibers within them shorten and get rotated. And they get rotated because as they shorten, they get bulged, and that forces the fibers to push outwards and rotate. That rotation is really good because instead of just needing fiber shortening, if they also rotate, notice the muscle shortens even further. So it shifts your power output. Doesn't improve peak power. It shifts your power output to higher speeds. So this fiber rotation is really important for high-speed muscle activation. And one hypothesis at the moment is you need the water to get that to happen. But you know what? Outside all that, right down at the cellular level, it matters too. It's been very well demonstrated that, again, when the myosin attaches to actin, it pulls, it detaches. When it detaches, it's no longer applying a force. So you either need it to get back quickly, or imagine if you could just prolong that stroke a bit more. Then on average, the myosins would be attached a little bit longer, and at any time, there would be more still pulling because they're pulling for longer. That means if you got more of them attached, you got more force. And it's very well demonstrated that if you put water into the cell, into the muscle fiber, myosin stays attached a bit longer. And the reason is because proteins have an electrical charge. They got a positive at one end and a negative at the other end. They're charged, and half the reason why they attach to each other is like opposite ends of a magnet. You have two different poles or two different charges and they attract. And that's what helps myosin get onto actin. So when it gets to this end, if you've got more attraction, it's harder for myosin to pull off, so it stays attached longer. Now, water, H2O, also has hydrogen, which is a positive, and two oxygens, which are negative. So it's also got a charge. It's got different poles. So you put a water molecule next to actin and myosin, and it affects that attractive charge. And it turns out that if you put lots of water in there, it stops myosin pulling off. The myosin can't pull off because it's too attracted to the actin. So the water seems to improve muscle force. And this has been known for a long time. We think that maybe things like creatine and warm up. When you warm up, you generate a bit of lactate, doesn't have to be much. You generate hydrogen ions, you generate all these other things. That draws water into the cell, makes it nice and swollen. And at the moment, we're doing experiments to see if we can look for associations between the water and the force. We haven't published them yet, but we have found those associations. So I hope to be able to publish those soon. So it does look like water mass is actually a really important for force, all the way through to higher speeds of force. So yeah, make sure you rehydrate fully. It could be really important.
Well, that's a brilliant explanation. Thank you.
Maybe the most important thing for your listeners is to start thinking about what's happening at the whole body level. Water water is one of them, but temperature is a huge one, which we should talk about. And of course, the neural activation part of it is also probably huge that we should talk about. What I want is for everyone to stop thinking about all these cool things that might be the 0.5 percenters and get back to the basics. Always think, what are we trying to achieve here? Let's go back to the idea then that in your warm-up, let's call it a warm-up, even though it's not just about temperature. The first thing that has to happen here is that we need to practice maximally activating the muscles. Even if I just do something like a bicep curl and I do the fastest, hardest activation possible once, and I look at how fast the force rises and I look at the peak force. Now, even if I wait a minute so that there's, no chance of a temperature rise because I did one quick contraction and then I sat around for another minute, so there'd be almost no effect on temperature a minute later. If I now activate a second time and I wait a minute and do another one, the only thing I'm really doing here is practicing the high speed maximal activation of the muscle. And if I put little electrodes on there and I record from the muscle, I can see an increase in both the rate and the height of the activation, the electrical work. If I use like an electrical or a magnet to stimulate the very part of my brain that would cause this muscle to twitch, I can see a bigger twitch or a bigger electrical activity. In other words, this whole pathway to the muscle has been upregulated or potentiated, if you like. Now, what's really important is that you're practicing maximal rapid activation. It's also important, though, that we're testing the same exercise we're training. And this is really important because it's not just that muscle that gets this brief, quick learning. It's all the supporting muscles, because it's even just doing this is super complicated, because as soon as I activate this muscle, a whole range of forces happen all through here that my brain has to know are about to happen. It has to pre-activate all this just to get this to work. In other words, if you practice a task with maximal effort, maximal rate of effort, you will learn that task and you will perform it better. And when we test 5 minutes later, 10 minutes later, we can still see that activation. In fact, one of my favorite studies was done back in 1998, and they deliberately stimulated the brain. So there was no voluntary opportunity here. And they recorded from the thumb muscle. And when they stimulate, the thumb might twitch like this. And they put a little accelerometer here to see how fast the muscle moves, but also what direction. Do you know what they did? They stimulate like heaps and heaps of times, and they see the muscle doing this. What they then did was they asked them to activate or practice in the other direction. So it's the thumb muscle, but it's the opposite muscle now works. They leave the stimulator right here. So when they re-stimulate it, it's exactly the same place. It should give you exactly the same outcome, but you know what? It didn't. Instead, the thumb went the wrong way. So literally, you stimulate the same part of the brain, but because you've just practiced going this direction, you've now increased the excitability, we call it, of that pathway. It's a short-term, lasts at least minutes, many minutes. Goes in the wrong direction. Now, if in that study, they recorded for the next half an hour, and it took something like 15, 20, 25 minutes for that stimulation to eventually cause a much more regular, appropriate activation. In other words, the practice you do in the tens of minutes completely affects it. Now, even if your brain was receiving the correct motor program from the pre-motor area, sending it to the bit that has to activate the motor area, even if it received the right info, what we're saying is you activate that part of the brain and it still gives you an inappropriate response. So somewhere in this part of the pathway, it's changing. So what we learn from these studies is you have to practice maximal activation, but you have to practice it perfectly coordinated with the skill. Now, in weightlifting, you might break the weightlifting skill down and do each phase of it first, and then build it all up and do some full practice lifts. But the most important thing that you can do as a weightlifter is literally do the motor control, the motor coordination warm up, already lifting to absolute maximum and going to reasonably heavy weight. Might not be the weight you use on the platform, but reasonably heavy. And if you do something else, you can seriously affect it.
So, Tony, would you have some examples of how warm-up could be constructed and how this skill practice could be used to then enhance performance?
Yeah, sure. I mean, within the limits of the fact that unfortunately, we probably don't have enough research actually looking at the whole warm-up, its construction and its outcomes, right? Is that we know that muscle temperature is really important. And I think we'll probably talk about that very briefly. Actually, let's just cover it now because it's so quick and easy.
Okay.
When you have an increase in muscle temperature, it comes from two things mainly. One is you get more blood flow, and the blood sitting deep in your body is really warm. So when it flows out to your muscles, that blood is warmer than your muscles because your muscles are on the periphery, so they're losing heat all the time. So you get a blood flow, and that warm blood warms your muscles. The second thing is your muscles are working, and when they're working, they're generating energy because all of your cell processes are not very efficient. And so every time they're happening, they're releasing lots of heat. And so everything warms up. And the good thing is between the blood flow and just that metabolic heat is that increases the rate at which some of your enzymes work, and particularly an important enzyme, an ATPase, which cleaves ATP apart and gives you energy for muscle contraction. It's really common that most, not all, but most of your enzymes work faster under slightly higher temperatures. And if those enzymes, which are basically little things that speed up chemical reactions, if those enzymes can speed up your chemical reactions, you can cross-bridge cycle faster. And so it makes sense that temperature improves performance, and it does it mostly by increasing the speed at which you can cycle, or therefore the speed at which your muscles shorten. So while the increase in water appears to be really a force-based mechanism, remember power is force times velocity, so that helps. The temperature appears to be more of a velocity-based mechanism. And this is really important to think about because in people doing really high-speed movements, or people who have lots of fast-twitch fibers where they should be capable of high speed, that increase in temperature should be more important. And just increasing the muscle temperature by 1 degree, which doesn't take a lot of contractions, can improve power by about 5%. I mean, 5% is massive, right? Do the math. If you could do, say, 10%, you'd run 100 meters like a whole second quicker. So 5% is a massive gain in power, right? So temperature is critical. We've already talked about motor control, so coordination and massive top or peak activation, temperature and water. And they're the three things that we really believe matter the most. So where does this leave us for a warm-up? Well, you can do a general warm-up if you like. I mean, if you just want to go for an easy run or sit on an exercise bike or sit on a rower because it's whole body and going to actually warm up more of the things, and you just do a 5-minute easy row or whatever, you can do that. That will elevate the temperature of the body, elevate the muscle temperature, increase blood flow. Perfect. But at some point, you have to start doing the lifting because only when you do that can you get maximal, highly coordinated activation practice. Of course, an Olympic lift is really complicated. So you might start off with just doing the deadlift portion of it, some press parts of it, you're walking around and you're just practicing all the different bits, making sure you feel like you've got your appropriate range of motion. If you want to do some higher range of motion stuff to improve your mobility briefly or do some stretching, yes, you can. I know that's another podcast, but you can do some brief stretching and that won't affect your weightlifting performance. But if it makes you feel like you're able to get in your positions better, then that will benefit performance. And then you got to keep on pulling the complex task together, and you got to keep on getting faster and faster until you're lifting a pretty good load at your absolute fastest effort through the full lift, because that's perfect practice. By the way, and this is where the research isn't so great, we know that mental imagery is really, really useful. What we probably don't know is if you do the mental imagery in addition to the perfect practice, does it augment performance more? Most of us who train in the gym say yes. If you're doing a heavy bench press, the very first rep is always better if you've just done some mental imagery. So we think mental imagery could be important. And that's why I'm sure some of your lifters go out onto the platform and the last thing they're doing is doing their internal imagery, right? So that's what a warm-up will do. It will make you feel better. It will give you the appropriate ranges of motion. It will increase your muscle temperatures. A light sweat is a nice place to be. It will then give you practice at a highly complicated skill, which, by the way, might require you to build it up from simple movements to the whole movement. And it will give you maximal rate of activation of your muscles, which is completely exceptionally important for weightlifting. That whole thing could take you half an hour, 45 minutes, depending how much time you leave between your practice lifts. By the way, in a lot of research then, if you look at research looking at PAPE, you're lucky if the warm-up lasts 5 to 10 minutes, even if they say a specific warm-up was done. So it's really important to read the research and say, is this actually a warm-up that I would do before a competition? And therefore, do I know whether this conditioning activity, this extra cool, sexy thing, is actually going to work on my day? And if you're not sure, you can test it yourself. Be your own test subject and see whether it works works for you, because everyone's different, right? And things are going to work differently for everyone. So what you need to do is replicate your competition in training and actually see which type of warm-up works best for you and whether something funky and cool is beneficial.
Sounds good. The other part in the research is that where we talked a little bit off camera is that research studies have responders and not responders, but not only that, people are responding to a different degree. So if we are running a study, we are usually reporting means for the group. So this is where, okay, overall, on average, this is what we are expecting to happen. But individual, maybe on this end or this end or anywhere in the middle, or even can be an outlier, so be somewhere else for whatever reason. So it is always important to, okay, this is what we see in research, but this is how it will relate to you. And you only know that after testing the protocol or the thing that was tested for yourself.
Yeah, perfect. So that's really important, because, it's really nice to think that your listeners are actually, jumping on Google Scholar and trying to find the research and talking to people about them and looking for themselves, right? That's a really good thing to do. So when you're doing that, there are a few things you need to watch out for. One of them you mentioned is that when we do research studies, we often tell you how on average everyone moved. We tell you something about the variability of that, but we're not always looking at individuals. We just say, oh, on average they did this, and yeah, there was a bit of variability there. Of course, what that really tells us is that everyone needs to actually look at that and go, it appears as though this might help, but until I test it myself under the right conditions, I'm never going to actually know if it helps me, because it could hinder you. And we see this a lot. We see that with certain strength training programs and certain endurance training programs, we have what we call non-responders. And some of them are not responding the way you would expect. And that's really important for you to know, right? For you. But there's another problem here. In some research studies, of course, researchers are aware of this problem, and they'll say, hey, look, there is a variability. I'm going to show you that there were some people who responded positively, and these people were below the average. They didn't respond positively. But that's also a big problem in research, because every test has an unreliability. It's not just the test here that is a little bit unreliable. It was also the first test, the pre-test, that was a bit unreliable. So now the change that you're looking for is doubly unreliable. And by the way, on the day, you are also unreliable. The subject themselves is unreliable, because they might have lost motivation at the end of the study, or they might have not been as motivated at the start of the study, or they were chatting to the researcher about something in the pre-testing, but at post-testing they were fully focused. And so humans themselves are unreliable, and all that unreliability is in there. So you can't just say, look, these people are non-responders because they didn't go up. The only way to know if they were non-responders, or if these people were responders, is to test them multiple times. At least 3, probably at least 4. And if they get the same response 4 times out of 4, that's probably their actual true response. So we got to, yes, think about the individual, but if you read a paper that just said there were responders and non-responders, you can't necessarily believe that that's the case. And even if you test it on yourself, you probably should test it at least twice. You'll know whether you were fully motivated, fully warmed up, same time of day, blah, blah, blah. At least do it twice, if not 3 times, to find out whether it is repeatably and reliably good or bad for you. Does that make sense?
Yes. Okay, one more aspect I wanted to ask you about is time frames. So what time frame would we expect for temperature, for water content, and for skill practice? How in minutes? So, if you're trying to make the perfect warm-up, how you should be thinking about how long the temperature will be lasting for, and how long the water content will be lasting for, or how...
This is a really good question. Do you know, I'm not aware of a single study that has properly done this, where we say, here is the full proper warm-up. It might be over half an hour of exactly what Olympic guys are doing, girls are doing before they go out on the platform at the Olympic Games. Now let's test and see how long certain things are lasting. You'd have to get them in several times, because you need a few different tests and they'll all affect each other, right? So it's not an easy study. You need good athletes willing to give up the time. You need to have the ability to do the tests, and you probably need to get people in multiple times to do different tests on different days to build up the full picture. I'm not aware of that being done. What I can tell you in our lab is that when we look at changes in muscle temperature, changes in water mass, we're doing it after just a few contractions. Just a few contractions are enough to increase temperature by a degree and a half. That's a lot. It's enough to detectably change water. We can see the muscle thickening. We look at how electricity passes through your muscles and we see it change. We know that therefore there's a water change. And it looks like it's lasting 8 to 10 minutes at least. So it means that if you finish your warm up and it takes a bit of time to get to the platform to do your lift, you're probably okay. But here's the thing. If you do a bigger amount of effort, so you do a harder warm up than just the few contractions we're doing in our experiments, if you're building up temperature over a slightly longer period of time, we do think that these effects are lasting even longer. So 15 or 20 minutes would not be unreasonable. So it looks like if you do your warm up out the back, by the time you come out the front, you've got most of it. But that doesn't mean you've got all of it, right? So the question is, should I be doing something in the 30 seconds or 1 minute before I actually stand on the platform? The answer is probably. Exactly what that is, hard to tell. Probably it's something that rapidly activates your nervous system and your water and your temperature, like a few vertical jumps. But we don't want it to be so specific that it can interfere. So one thing you might do is just a couple of quick vertical jumps to get the temperature and the water back up. But of course, when you first get it out there, the next thing you're going to do is the mental imagery to make sure that your motor pattern has just been gone through in your brain. Now, I have to stress, we have never done the research and I haven't seen a study that has done this idea of a few jumps and then mental imagery and checked how that then makes you behave. Other things people are doing is trying to maintain passive temperature and a bit of water flow by doing the warm up and then putting hot stuff on them or putting extra clothing on that you only take off just as you're about to walk out. So the key is to find ways to maintain muscle temperature whilst not doing something that might interfere with your motor pattern. So passive heating could be really good after you finish your full warm up just before you walk out onto the stage.
That's very useful. Thank you.
Sorry, I don't have all the perfect answers, but that's science, isn't it?
Yeah, I think it gives us something to try. So thank you. So I will give you an opportunity to bring it all together. So what would be your take-home message for coaches who try to prime the athletes or try to give them the best chance to perform specifically in power and strength sports? So 1 repetition maximum. What will be your take-home message?
Okay. Well, the take home is that most of it, of course, is in proper training, nutrition, sleep, and stress management before you even get there. All the basics, right? The basics are the key. Without talking about priming, just the immediate sort of warm up within the hour before competition or so, just go back to the basics of what a full, comprehensive, perfect warm up should have to the best of our current understanding. And that is muscle temperature, probably water, maximal activation, perfect coordination. And of course, the psychology of being in that perfect state of psychology where you're not too stressed and not too understressed, which we haven't talked about. Once you do that and get that about right, at the moment that the possibility is that there are some little tricks and weird conditioning activities we might do that can enhance performance more.
All right, I think it's a good news because you always look for tiny things, but really, if you get the basics right, if you warm up to a certain temperature and you hydrate it properly, you practice skill with intention of being fast and powerful and explosive. At skill like Olympic weightlifting, snatch or clean and jerk, where these are the very complex but also fast movements. So if you do that, you're mostly there. So I think it's a good news.
Exactly. And practice that process over and over again. And once you like the process, that will also help you with your psychology, right? You won't get too nervous because you've been through the process a million times. You're just repeating it. But you'll be motivated because motivating is part of your process. And as your lifters know, when they're highly motivated but appropriate, that's when they do their best because you need a massive activation of the muscles and a lot of muscles. It's not just the knee extension, right? It really matters.
I interviewed Tom Smiley on imagery specifically for weightlifting and how to do it from I want to do it to how to actually implement it. So I think I may pair your interview with his so that people can get this full combo physiology plus the psychological part. I think
Yeah, nice. Get the whole package. Perfect. Sounds good.
Awesome. So I have two short questions to finish. The first one is, what is your favorite exercise, you personally?
In the gym, that's a really good question. I have to say bench press because it's just the one thing where it has to always come down to a certain point, always up to a certain point. You can't fake it. It is what it is. Unfortunately, shoulders are starting to get a bit sore these days. Out of the gym, I'm a sprint runner and I love nothing more than the feeling of flowing during a high speed run. It feels amazing. It feels like I'm flying. And so I can't better than a nice sprint run.
Awesome. And the last question is where people can find you if they want to follow your work, learn more, or ask a question.
Well, of course, you can type in Blazevich into Google Scholar and find all the research because there aren't too many Blazeviches. My Twitter or X handle is Tony Blazevich. I think it's one word, at wherever. And that'd be the same for Instagram, although I don't use Instagram a lot. So LinkedIn should be all the same thing. If you search for Tony Blazevich, you should be able to find everything.
Awesome, Tony. Thank you so much for the day. It was a pleasure.
My pleasure. Good to chat to you. Good luck with everything. Cheers.
Thank you.